You know, if Shakespeare had been an astronomer, he'd have said that there is a tide in the affairs of the universe, and on such a full sea are we now afloat. He would have been right. You might just think of tides as the ocean going in and out every day. But in fact, what astronomers call tides are a subtle but inexorable force that have literally shaped most objects in the universe. And to understand tides, we start with gravity. Gravity is a force, and it weakens with distance. An important thing to note is that we measure gravity from the center of mass of an object, not its surface. One way to think of the center of mass of an object is the average position in an object of all its mass. For an evenly distributed sphere, that's its center. Right now, unless you're an astronaut, you're about 6,400 kilometers from the center of the Earth. If you stand up, your head is a couple of meters farther away from the Earth's center than your feet. Since gravity weakens with distance, the force of Earth's gravity on your head is an eensy-weensy bit less than it is on your feet. How much less? A mere 0.00005%. And that's way too small for you ever to notice. But what if you were taller? Well, the taller you are, the farther your head is from the Earth's center and the weaker force it will feel. If you were, say, about 300 kilometers tall, the force of gravity would drop by about 10% at your head. That probably would be enough to notice if you weren't dying from asphyxiation and, being 300 kilometers tall. This change in the force of gravity over distance is what astronomers call the tidal force. When you have a massive object affecting another object with its gravity, its tidal force depends on several factors. For one thing, it depends on how strong the gravity is from the first object. The stronger the force of gravity, the stronger the tidal force will be on the affected object. It also depends on how wide the affected object is. The wider it is, the more the force of gravity from the first object changes across it, and the bigger the tidal force. Finally, it depends on how far the affected object is from the first object. The farther away the affected object is, the lower the tidal force will be. Tides depend on gravity, and if gravity is weaker, so is the tidal force. The overall effect of the tidal force is to stretch an object. You're applying a stronger force on one end than you are on the other, so you're pulling harder on one end. That'll stretch it. And this is where tidal forces become very important. Look at the moon. It has gravity, but much less than the Earth because it's less massive. It's 380,000 kilometers away, so the gravitational force it has on you is pretty small. And you're pretty small compared to that distance, just a couple of meters long from head to feet. But the Earth is big. It's nearly 13,000 kilometers across. That means the side of the Earth facing the moon is about 13,000 kilometers closer to the moon than the other side of the Earth. This is a pretty big distance, enough for tides to become important. The side of the Earth facing the moon is pulled harder by the moon than the other side of the Earth, so the Earth stretches. It becomes ever so slightly football-shaped, like a sphere with two bulges, one pointing toward the moon and one pointing away. This is probably the weirdest thing about tidal forces. You might expect only one bulge on the side of the Earth facing the moon. But remember, we measure gravity from the centers of objects. The side of the Earth facing the moon feels a stronger pull toward the moon than the Earth's center, so it's pulled away from the center. But the side facing away from the moon feels a weaker force toward the moon than the Earth's center. This means the center of the Earth is being pulled away from the far side. This is exactly the same as if the far side is being pulled away from the center. And that's why you get two bulges on opposite sides of the Earth. The tidal force is therefore strongest on the sides of the Earth facing toward and away from the moon, and weakest halfway in between them on each side. A lot of the Earth is covered in water, and water responds to this changing force, this stretching. The water bulges up where the tidal force is strongest on opposite sides of the Earth. If there's a beach on one of those spots, the water will cover it, and we say it's high tide. If a beach is where the tidal force is low, the water's been pulled away from it, and it's low tide. But wait a second. The Earth is spinning. If you're on a part of the Earth facing the moon, you're at high tide. 6 hours later, a quarter of a day, the Earth's rotation has swept you around to the spot where it's low tide. 6 hours after that, you're at high tide again, and then another 6 hours later, you're at low tide for the second time that day. Finally, a day after you started, you're back at high tide once more. And that's why we have 2 high tides and 2 low tides every day. Very generally speaking, the ocean tide causes the sea level to rise and fall by a meter or 2 every day. Incidentally, the solid Earth can bulge as well. It's not as fluid as water, but it can move. The tidal force stretches the solid Earth by about 30 centimeters. If you just sit in your house all day, you move up and down by about that much, twice. Like the saying goes, a rising tide lifts all surfaces. The Earth's spin has another effect. Lag in the water flow means the water can't respond instantly to the tidal force from the moon. The Earth's spin actually sweeps the bulges forward a bit along the Earth. So picture this. The bulge nearest the moon is actually a bit ahead of the Earth-Moon line. That bulge has mass. Not a lot, but some. Since it has mass, it has gravity, and that pulled on the moon. It pulls the moon forward in its orbit a bit, like pulling on a dog's leash, accelerating it. The moon responds to this tug by going into a higher orbit. The moon is actually moving away from the Earth. The rate of recession of the moon has been measured, and it's something like a few centimeters per year, roughly the same speed your fingernails grow. Now get this. The moon has gravity. Just as the bulge is pulling the moon ahead, the moon is pulling the bulge back, slowing it down. Because of friction with the rest of the Earth, this slowing of the bulge is actually slowing the rotation of the Earth itself, making the day longer. The effect is small, but again, it's measurable. Okay, let's get a little change of perspective. Everything I've said about the moon's tidal effect on the Earth works the other way too. The moon feels tides from the Earth, and they're pretty strong because the Earth is more massive and has more gravity than the moon. Just like Earth, there are two tidal bulges on the moon, one facing the Earth and one facing away. Long ago, the moon was closer to the Earth and spinning rapidly. The moon's tidal bulges didn't align with the Earth, and the Earth's gravity tugged on them, slowing the moon's spin and moving it farther away. As it moved farther away, the time it took to orbit once around the Earth increased. Its orbital period got longer. Eventually, the lengthening rotation of the moon matched how long it took to go around the Earth. When that happened, the axis of the bulges pointed right at the Earth. That's why the moon only shows one face to us. It spins once per month and goes around us once per month. If it didn't spin at all over that month, we'd see the entire lunar surface. But since it does spin once per orbit, we only ever see one face. This is called tidal logging, and it's worked on nearly every big moon in the solar system. Tides from their home planet have matched their spin and orbital period. These moons all show the same face toward their planet. Now, wait a second. If the moon has gravity, which causes tides, and is the root cause behind all these shenanigans, what about the sun? It's even bigger than the moon. Tides depend on the gravity from an object and your distance from it. The sun is far more massive than the moon, but much farther away. These two effects largely cancel each other out. And when you do the math, you find the sun's tidal force on the Earth is just about half that of the moon's. The way the sun's tidal force and the moon's tidal force interact on Earth depends on their geometry, which changes as the moon orbits us. At new moon, the Earth, moon, and sun are in a line. The moon's tidal force aligns with the sun's, reinforcing it. This means we get an extra high tide and an extra low tide on Earth. We call this the springtime. When the moon is at first quarter, the tidal bulge from the moon is 90 degrees around from the sun's. High tide from the moon overlaps low tide from the sun. We get a slightly lower high tide and a slightly higher low tide. We call those neap tides. The pattern repeats when the moon is full. The moon, Earth, and sun fall along a line again, and we get spring tides. A week later, the moon is moved around, and we get neap tides again. Not only that, the moon orbits the Earth on an ellipse. When it's closest to us, we feel a stronger effect. If that also happens at new or full moon, we get an added kick to the spring tides. This is called the Proxygian tide and can lead to flooding in low-lying areas. Unless you live on the coast, I bet you had no idea tides were so complex. Tides are universal. They work wherever there's gravity. If two stars orbit each other, each raises a tide in the other. Just like the Earth and moon, that can slow their spin and increase their separation. Many planets orbiting other stars may be tidally locked to those stars. Near a black hole, where the gravity is incredibly intense, the tides are so strong they would pull you like taffy into a long, thin string. Astronomers call this effect spaghettification. No, seriously, that's what we call it. Today you learned that tides are due to the changing force of gravity over distance. The strength of the tidal force from an object depends on the gravity of the object and the size of and distance to the second object. Tides raise two bulges in an object, creating two high tides and two low tides per day on Earth. Tides have slowed the Earth's rotation, moved the moon away from the Earth, and locked the moon's rotation in orbit so that the moon always has one side facing us. So, tide goes in, tide goes out. The sun is a star. That's a profound statement, and one that's not really all that obvious. Those little sparks in the night sky are pretty, but don't look anything at all like the hot, blazing orb that lights up our days. It was a pretty remarkable intellectual leap to understand the sun and the stars are just different flavors of the same kind of object. The only difference is that the sun is close, but the stars are terribly far away, so they're fainter. Right away, let's clear up a misconception. A lot of people say the sun is a middle-sized average star, but that's not fair. Sure, it's somewhere in the middle of the size range of stars, but the vast majority of stars are dim red dwarfs, far smaller than the sun. By size and number, the sun ranks in the top 10% of stars in the galaxy. In our solar system, it's clearly the dominant object, brighter, more massive, and more influential than anything else. But what is it? The sun is essentially a big hot ball of mostly hydrogen gas. It's 1.4 million kilometers across, more than 100 times the Earth's diameter, and big enough that well over 1 million Earths could fit inside of it. And it's massive, 300,000 times more massive than the Earth, a staggering 2 octillion tons of gas. But if we want to truly understand the sun, we have to look into its heart. At the very core of the sun, conditions are hellish. The pressure is a crushing 260 billion times the Earth's atmospheric pressure, and it's a searing 15 million degrees Celsius. Under those conditions, hydrogen is completely ionized, which means the electrons in the atoms are stripped from their protons. This makes the core a thick soup of ultra-hot subatomic particles. In fact, the protons are squeezed together so hard by the octillions of tons of mass lying on top of them that an amazing thing happens. They fuse together. Through a complicated series of steps, the hydrogen atoms fuse together to form the heavier element helium. Along the way, some of the nuclear energy stored in those atoms is released. That amount of energy is described by Einstein's famous equation E=mc², which states that mass can be converted into energy and vice versa. Atoms are pretty small though, so each helium atom made in the sun's core generates only a tiny bit of energy, but a lot of helium atoms are made. A lot. Get this. Every second of every day, the sun converts 700 million tons of hydrogen into 695 million tons of helium. The missing 5 million tons, the equivalent weight of 15 Empire State Buildings, is converted into energy. And that's a lot of energy. Enough, in fact, to power a star. It's equivalent to detonating 400 billion 1 megaton nuclear bombs every single second. That's millions of times the entire nuclear arsenal of our planet, every second. And that's why, even from a distance of 150 million kilometers, the sun is so bright, you can't even look at it. Even from that distance, its heat can be felt on your skin when you stand outside. Hydrogen fusion occurs in the core of the sun. The energy released heats the gas above the core, but not quite enough to fuse hydrogen into helium. Further from the sun's center, the gas becomes less dense. And at some point, the heat pouring up from below makes the gas buoyant. It rises in the same way a hot air balloon on Earth rises. This process is called convection, and it's an efficient way of transferring heat. Huge columns of rising hot gas stretch hundreds of thousands of kilometers high, bringing the sun's internal heat to the surface. The gas then cools and sinks back down into the interior. We can actually see the tops of these columns packed together across the sun's face. Above the convecting layer is a much thinner, cooler layer very near the sun's surface called the photosphere, or literally the sphere of light. This is where the density of the material inside the sun gets thin enough that it becomes transparent. Light can shine right through it. At this point, the energy from inside the sun is free to travel into space. It's this light that we see when we look at the sun. The sun is a gas and doesn't have a solid surface, but the gas in the photosphere thins so rapidly compared to the sun's huge size that you can think of it as the sun's surface. And there's one final layer above that, the ethereally thin corona, sort of like the sun's atmosphere. It's less than 1% as dense as the photosphere, but actually much hotter. Temperatures there can reach over 1 million degrees. However, it's so thinly dispersed that it's incredibly faint and can only be seen during a total eclipse or using special telescopes that block the intense light from the sun itself. The corona extends for millions of kilometers, and in a sense, it doesn't actually end. The corona merges into what's called the solar wind, a stream of subatomic particles moving away from the sun. It blows out in all directions, though mostly along the sun's equator. The speed of the wind is usually well over 1 million kilometers per hour. Yes, seriously, and can reach speeds even much higher than that. When hydrogen fuses into helium in the sun's core, the energy is released in the form of light. This light immediately smacks into a subatomic particle, which absorbs it, converts a little bit of the energy into motion, and re-emits the light with a little bit less energy. The light works its way out of the sun this way, losing energy every time it encounters a particle, until eventually it gets to the surface and is free to fly away into the universe as a much lower energy photon of visible light. So how long does this process take? I've seen different numbers for it, some as much as 1,000,000 years. But a lot of those calculations don't model conditions inside the sun accurately. For example, they don't take into account the gas convecting for hundreds of thousands of kilometers. More modern calculations show that it takes closer to 100,000 or 200,000 years for the energy to work its way out. That's still a pretty long time. The light you see from the sun now got its start in the sun's core around the time Homo sapiens first appeared in Africa. The sun's surface is, to put it kindly, a mess. And the key to that mess is magnetism. I've been saying the sun is made of gas, but that's not entirely accurate. It's so hot inside the sun that electrons are stripped from their parent atoms in the gas, creating what's called a plasma, a gaseous soup of charged particles. We'll learn more about that in a later episode. But what's important now is the fact that a moving electric charge generates a magnetic field. The interior of the sun is essentially all charged particles in motion. Convection, coupled with the sun's rotation, sets up rivers or streams of plasma inside the sun, each generating and carrying its own magnetic field. When this plasma reaches the sun's surface, their magnetic fields do too. Maybe you've seen those looping arcs of magnetism around a bar magnet when it affects iron filings on a piece of paper. The solar magnetic fields are like that, except there can be zillions of them all over the sun's surface, where they can interact and even get tangled up. When the plasma reaches the surface, it cools. But if the magnetic loops tangle up, they prevent the plasma from sinking back down into the sun, like a knot in a shoelace prevents it from going through the eyelet on your shoe. Plasma shines because it's hot, but as it cools, it dims. It sits on the surface dimming, producing a dark spot on the surface of the sun, which we call a sunspot. Sunspots can be huge. They commonly dwarf the entire Earth, and some are so big they can be seen without using a telescope, as long as you're wearing adequate eye protection, of course. Around the edges of sunspots, the magnetic field lines are concentrated. This can energize the plasma even further, heating it up. This creates a bright rim around sunspots called faculae, Latin for little torch. The dark parts of sunspots dim the overall light from the sun, but faculae can be so intense they compensate for that and even add more light. Ironically, sunspots actually increase the energy output of the sun. Plasma on the sun's surface can flow along these magnetic loops too. This can create huge arcs of material called prominences or filaments, stretching for hundreds of thousands of kilometers across the sun, looking like fiery arches. We think these magnetic field lines are feeding energy from the sun's surface into the corona, which is why it's so much hotter. It's not exactly clear how this happens, but scientists are following several leads right now. This long-standing mystery may soon be solved. Magnetic fields on the sun also have a huge amount of energy stored in them. You can think of them like very tightly wound and very stiff springs. But remember, these magnetic field lines get tangled up. If conditions are right, they can actually snap, in essence creating a gigantic short circuit. When this happens, all that vast energy stored in the lines explodes outwards all at once in an event we call a solar flare. Even an average solar flare is mind-crushingly powerful. A big one can release as much as 10% of the entire sun energy output. This explosion blasts out high-energy light and launches material off the surface of the sun at high speeds, sending it into interplanetary space. Another type of solar eruption is called a coronal mass ejection, or CME. It's similar to a flare, but if a flare is like a tornado, intense and localized, a CME is like a hurricane, huge and strong. Like flares, they form when tangled magnetic field lines erupt, blasting out energy, but they occur higher off the sun's surface. Both flares and CMEs eject material into space. Billions of tons of it, in fact. This blast of debris can hit the Earth, and when it does, there can be profound effects. Our atmosphere absorbs the high-energy light, protecting us. Also, the subatomic particles are generally deflected by the Earth's magnetic field, so we're okay. But if conditions are right, the Earth's magnetic field can interact with the particles. Massive numbers are funneled down into Earth's atmosphere near the poles, causing the air to glow. This is what we call the aurora, or the northern and southern lights. Depending on the shape of the magnetic field, the auroras can form spectacular multicolored ribbons and sheets. Not all the effects are benign, though. As the magnetic fields interact, they can induce very strong currents of electricity in the Earth's crust. This can overload power grids, causing blackouts. In 1989, Quebec suffered a massive power outage from a solar storm. The very first such storm ever detected was in 1859, and it was also the most powerful ever seen. If an event like that were to happen today, it could cause worldwide blackouts and potentially be very damaging. Satellite electronics would be fried too, and we depend on those satellites for our modern civilization. In fact, in 2012, a huge storm, probably the equal of the 1859 event, blasted away from the sun in another direction, missing the Earth. Had it hit us, well, you probably wouldn't be watching this video now. We'd still be recovering. This is why studying the sun is so important. We depend on it for light and heat and the very basis of life itself, but it's entirely capable of knocking our society to its knees. Understanding it is critical to our future. The sun is the 2 octillion-ton gorilla in the room. We need to respect that. Today you learned that the sun is a star powered by nuclear fusion in its core. Hot plasma moves inside the sun, creating magnetic fields, which in turn can create sunspots, solar flares, and coronal mass ejections. These events can generate aurorae on Earth, cause power blackouts, and damage satellites. This episode is brought to you by Square.
All right, so skipping around a little bit here, they do have a video for each of the planets. They've got asteroids, they've got comets. Yeah, please do check those out if you're more interested in this. There's also one on telescopes. How to make a hard cut there. Next one we're looking at is distances.
Oh, hey, sorry, I don't mean to be rude. I'm just trying to figure out how far away my thumb is. How? Parallax. Centuries ago, people thought the stars were holes in a huge crystal sphere letting through heavenly light. It wasn't clear just how big the sphere was, but it was pretty dang big. I have some sympathy for them. By eye, and for all intents and purposes, the stars are infinitely far away. If you drive down a road, you'll see nearby trees flying past you, but distant mountains move more slowly. The moon is so far, it doesn't seem to move at all compared to nearby objects, and it's easy for your brain to think it's much closer, smaller, and actually following you, which is a bit creepy. Sometimes people even think it's a UFO tailing them. Finding the distance to something really far away is tough. It's not like you can just pace off the distance. Or can you? The ancient Greeks knew the Earth was round, and there are lots of ways to figure that out. For example, ships sailing over the horizon seem to disappear from the bottom up, as you'd expect, as they slip around the Earth's curve. But how big is the Earth? Over 2,000 years ago, the Greek philosopher Eratosthenes figured it out. He knew that at the summer solstice, the sun shone directly down a well in the city of Syene at noon. He also knew that at the same time, it was not shining straight down in Alexandria, and could measure that angle. There's a legend that he paid someone to pace off the distance between the two cities, so he could find the distance between them. But more likely, he just used the numbers found by earlier surveying missions. Either way, knowing the distance and the angle, and applying a little geometry, he calculated the circumference of the Earth. His result, a little over 40,000 kilometers, is actually amazingly accurate. For the very first time, humans had determined a scale to the universe. That first step has since led to a much, much longer journey. Once you know how big the Earth is, other distances can be found. For example, when there's a lunar eclipse, the shadow of the Earth is cast on the moon. You can see the curve of the Earth's edge as the shadow moves across the moon. Knowing how big the Earth is and doing a little more geometry, you can figure out how far away the moon is. Also, the phases of the moon depend on the angles and distances between the Earth, moon, and sun. Using the size of the Earth as a stepping stone, Aristarchus of Samos was able to calculate the distances to the moon and the sun, as well as their sizes. That was 2,200 years ago. His numbers weren't terribly accurate, but that's not the important part. His methods were sound, and they were used later by great thinkers like Hipparchus and Ptolemy to get more accurate sizes and distances. They actually did pretty well, and all over 1,000 years before the invention of the telescope. And I think it also says a lot that these ancient thinkers were willing to accept a solar system that was at least millions of kilometers in size. But at this point, things got sticky. Planets are pretty far away and look like dots. Our methods for finding distances failed for them, for a while at least. In the 17th century, Johannes Kepler and Isaac Newton laid the mathematical groundwork of planetary orbits, and that in turn made it possible, in theory, to get the distances to the planets. But there was a catch. When you do the math, you find that measuring the distances to the other planets means you need to know the distance from the Earth to the Sun accurately. For example, it was known that Jupiter was about 5 times farther from the Sun than the Earth was, but that doesn't tell you what it is in kilometers. So how far away is the Sun? Well, they had a rough idea using the number found by the Greeks, but to be able to truly understand the solar system, they needed a much more accurate value for it. To give you an idea of how important the distance from the Earth to the Sun is, they gave it a pretty highfalutin name, the Astronomical Unit, or AU. Mind you, not an astronomical unit, the one. That's how fundamental it is to understanding everything. A lot of methods were attempted. Sometimes Mercury and Venus transit or cross the face of the Sun. Timing these events accurately could then be used to plug numbers into the orbital equations and get the length of an AU. Grand expeditions were sent across the globe multiple times to measure the transits and didn't do too badly. But our atmosphere blurs the images of the planets, putting pretty big error bars on the timing measurements. The best they could do was to say the AU was 148,510,000 kilometers, plus or minus 800,000 kilometers. That's good, but not quite good enough to make astronomers happy. Finally, in the 1960s, astronomers used radio telescopes to bounce radar pulses off of Venus. Since we know the speed of light extremely accurately, the amount of time it takes for the light to get to Venus and back could be measured with amazing precision. Finally, after all these centuries, the astronomical unit was nailed down. It's now defined to be 149,597,870.7 kilometers. So there. The Earth orbits the Sun on an ellipse, so think of that as the average distance of the Earth from the Sun. Knowing this number unlocked the solar system. It's the fundamental meter stick of astronomy and the scale we use to measure everything. Having this number meant we could predict the motions of the planets, moons, comets, and asteroids. Plus, it meant we could launch our probes into space and explore these strange new worlds for ourselves, see them up close, and truly understand the nature of the solar system. And it's even better than that. Knowing the astronomical unit meant unlocking the stars. We have 2 eyes, and this gives us binocular vision. When you look at a nearby object, your left eye sees it at a slightly different angle than your right eye. Your brain puts these 2 images together, compares them, does the geometry, and gives you a sense of distance to that object. And you thought your teacher lied when she said math was useful in everyday life. We call this ability depth perception. You can see it for yourself by doing the thumb thing. As you blink one eye and then the other, your thumb appears to shift position relative to more distant objects. That shift is called parallax. The amount of shift depends on how far apart your eyes are and how far away the object is. If you know the distance between your eyes, we'll call this the baseline. Then you can apply some trigonometry and figure out how far away the object is. If the object is nearby, it shifts a lot. If it's farther away, it shifts less. It works pretty well, but it does put a limit on how far away we can reasonably sense distance with just our eyes. Stars are a bit beyond that limit. If we want to measure their distance using parallax, we need a lot bigger baseline than the few centimeters between our eyes. Once astronomers figured out that the Earth went around the Sun rather than vice versa, they realized that the Earth's orbit made a huge baseline. If we observe a star when the Earth is at one spot, then wait 6 months for the Earth to go around the Sun to the opposite side of its orbit and observe the star again, then in principle, we can determine the distance to the star, assuming we know the size of the Earth's orbit. That's why knowing the length of the astronomical unit is so important. The diameter of Earth's orbit is about 300 million kilometers, which makes for a tremendous baseline. Hooray! Except, oops, when stars were observed, no parallax was seen. Was heliocentrism wrong? No. It's just that stars are really and truly far away, much farther than even the size of Earth's orbit. The first star to have its parallax successfully measured was in 1838. The star was 61 Cygni, a bit of a dim bulb, but it was bright enough and close enough for astronomers to measure its shift in apparent position as the Earth orbited the Sun. 61 Cygni is about 720,000 astronomical units away. That's a soul-crushing distance, well over 100 trillion kilometers. In fact, that's so far that even the Earth's orbit is too small to be a convenient unit. Astronomers came up with another one, the light year. That's the distance light travels in a year. Light's pretty fast and covers about 10 trillion kilometers in a year. It's a huge distance, but it makes the numbers easier on our poor ape brains. That makes 61 Cygni a much more palatable 11.4 light years away. Astronomers also use another unit called a parsec. It's based on the angle a star shifts over the course of a year. A star 1 parsec away will have a parallax shift of 1 arcsecond, 1/3600th of a degree. That distance turns out to be about 3.26 light years. As a unit of distance, it's convenient for astronomers, but it's a terrible one if you're doing the Kessel run. Sorry, Han. The nearest star to the sun we know of, Proxima Centauri, is about 4.2 light years away. The farthest stars you can see with the naked eye are over 1,000 light years distant, but the vast majority are within 100 light years. Space-based satellites are used now to accurately find the distance to hundreds of thousands of stars. Still, this method only works for relatively nearby stars, ones that are less than about 1,000 light years away. But once we know those distances, we can use that information on more distant stars. How? Well, like gravity, the strength of light falls off with the square of the distance. If you have two stars that are the same intrinsic brightness, giving off the same amount of energy, and one is twice as far as the other, it will be 1/4 as bright. Make it 10 times farther away, it'll be 1/100th as bright. So if you know how far away the nearer one is by measuring its parallax, you just have to compare its brightness to one farther away to get its distance. You have to make sure they're the same kind of star. Some are more luminous than others. But thanks to spectroscopy, we can do just that. A star's distance is the key to nearly everything about it. Once we know how far it is, and we can measure its apparent brightness, we can figure out how luminous it is, how much light it's actually giving off. And its spectrum tells us its temperature. With those in hand, we can determine its mass and even its diameter. Once we figured out how far away stars are, we started to grasp their true physical nature. This led to even more methods of finding distances. The light given off by dying stars, exploding stars, stars that literally pulse, get brighter and dimmer over time. All of these and more can be used to figure out how many trillions of kilometers of space lie between us and them. And we see stars in other galaxies, which means we can use them to determine the actual size and scale of the universe itself. And all of this started when some ancient Greeks were curious about how big the Earth was. Curiosity can take us a great distance. Today you learned that ancient Greeks were able to find the size of the Earth, and from that, the distance to and the sizes of the moon and sun. Once the Earth-Sun distance was found, parallax was used to find the distance to nearby stars, and that was bootstrapped using brightness to determine the distances to much farther stars. Crash Course Astronomy is produced in association with PBS.
All right, last one today. Stars.
Twinkle, twinkle, little star. Oh, I know who you are. At first glance, stars pretty much all look alike. Twinkly dots scattered across the sky. But as I talked about in episode 2, when you look more closely, you see differences. The most obvious is that some look bright and some faint. As I said then, sometimes that's due to them being at different distances, but it's also true that stars emit different amounts of light, too. If you look through binoculars or take pictures of them, you'll see that they're all different colors, too. Some appear white, some red, orange, blue, and for a long time, the reason for this was a mystery. In the waning years of the 19th century, astrophotography was becoming an important scientific tool. Being able to hook a camera up to a telescope and take long exposures meant being able to see fainter objects, revealing previously hidden details. It also meant that spectroscopy became a force. Say it with me now. For science! A spectrum is the result when you divide the incoming light from an object into individual colors or wavelengths. This reveals a vast amount of physical data about the object. But in the late 1800s, we were only just starting to figure that out. Interpreting stellar spectra was a tough problem. The spectrum we measure from a star is a combination of two different kinds of spectra. Stars are hot, dense balls of gas, so they give off a continuous spectrum. That is, they emit light at all wavelengths. However, stars also have atmospheres, thinner layers of gas above the denser inner layers. These gases absorb light at specific wavelengths from the light below, depending on the elements in them. The result is that the continuous spectrum of a star has gaps in it, darker bands where different elements absorb different colors. At first, stars were classified by the strengths of their hydrogen lines. The strongest were called A stars, the next strongest B, then C, and so on. But in 1901, a new system was introduced by spectroscopist Annie Jump Cannon, who dropped or merged a few of the old classifications and then rearranged them into one that classified stars by the strengths and appearances of many different absorption lines in their spectra. A few years later, physicist Max Planck solved a thorny problem in physics, showing how objects like stars give off light of different colors based on their temperature. Hotter stars put out more light at the blue end of the spectrum, while cooler ones peaked in the red. Around the same time, Bengali physicist Meghnad Saha solved another tough problem: how atoms give off light at different temperatures. 2 decades later, the brilliant astronomer Cecilia Payne-Gaposchkin put all these pieces together. She showed that the spectra of stars depended on the temperatures and elements in their atmospheres. This unlocked the secrets of the stars, allowing astronomers to understand not just their composition, but also many other physical traits. For example, at the time, it was thought that stars had roughly the same composition as the Earth. But Payne-Gaposchkin showed that stars were overwhelmingly composed of hydrogen, with helium as the second most abundant element. The classification scheme proposed by Cannon and decoded by Payne-Gaposchkin is still used today, and arranges stars by their temperature, assigning each a letter. Because they were rearranged from an older system, the letters aren't alphabetical. So the hottest are O-type stars, slightly cooler are B, followed by A, F, G, K, and M. It's a little weird, but many people use the mnemonic, "Oh, be a fine guy, kiss me," or "Oh, be a fine girl, kiss me," to remember it, which was dreamed up by Annie Jump Cannon herself. Each letter grouping is divided into 10 subgroups, again according to temperature. We've also discovered even cooler stars in the past few decades, and these are assigned the letters L, T, and Y. The Sun has a surface temperature of about 5,500 degrees Celsius and is a G2 star. A slightly hotter star would be a G1, and a slightly cooler star a G3. Sirius, the brightest star in the night sky, is much hotter than the Sun and is classified as an A0. Betelgeuse, which is red and cool, is an M2. Stars come in almost every color of the rainbow. Hot stars are blue, cool stars red. In between, there are orange and even some yellow stars. But there are no green stars. Look as much as you want, and you won't find any. It's because of the way our eyes see color. A star can put out lots of green light, but if it does, it'll also emit red, blue, and orange. And our eyes mix those together to form other colors. A star can actually emit more green light than any other color, but we'll wind up seeing it as white. How do I know? Because if you look at the Sun's spectrum, it actually peaks in the green. Isn't that weird? The Sun puts out more green light than any other color, but our eyes see all the mixed colors together as white. Wait, what? White? You may be thinking the Sun is actually yellow. Not really. The light from the Sun is white, but some of the shorter wavelengths like purple and blue and some green get scattered away by molecules of nitrogen in our air. Those appear to be coming from every direction but the Sun, which is why the sky looks blue. The Sun doesn't emit much purple, so the sky doesn't look purple, and the green doesn't scatter as well as blue. That gives the Sun a yellowish tint to our eyes. And looking at the Sun is painful anyway, so it's hard to accurately gauge what color it appears. That's also why sunsets look orange or red. You're looking through more air on the horizon to see the Sun, so all the bluer light is scattered away. So we can use spectra to determine a lot about a star. But if you combine that with knowing a star's distance, things get amazing. You can measure how bright the star appears to be in your telescope, and by using the distance, you can calculate how much energy it's actually giving off, what astronomers call its luminosity. An intrinsically faint light looks bright if it's nearby, but so does a very luminous light far away. By knowing the distance, you can correct for that and figure out how luminous the objects actually are. This was, no exaggeration, the key to understanding stars. A lot of a star's physical characteristics are related. Its luminosity depends on its size and temperature. If two stars are the same size, but one is hotter, the hotter one will be more luminous. If two stars are the same temperature, but one is bigger, the bigger one will be more luminous. Knowing the temperature and distance means knowing the stars themselves. Still, it's a lot of data. A century ago, spectra were taken of hundreds of thousands of stars. How do you even start looking at all that? The best way to understand a large group of objects is to look for trends. Is there a relationship between color and distance? How about temperature and size? You compare and contrast them in as many ways possible and see what pops up. I'll spare you the work. A century ago, astronomers Einar Hertzsprung and Henry Norris Russell made a graph in which they plotted a star's luminosity versus its temperature. When they did, they got a surprise, a very strong trend. This is called an HR diagram, after Hertzsprung and Russell. It's not an exaggeration to call it the single most important graph in all of astronomy. In this graph, really bright stars are near the top, fainter ones near the bottom. Hot blue stars are on the left, and cool red stars on the right. The groups are pretty obvious. There's that thick line running diagonally down the middle, the clump to the upper right, and the smaller clump to the lower left. This took a long time to fully understand, But now we know this diagram is showing us how stars live their lives. Most stars fall into that thick line, and that's why astronomers call it the main sequence. The term is a little misleading. It's not really a sequence per se, but as usual in astronomy, it's an old term and we got stuck with it. The reason the main sequence is a broad, long line has to do with how stars make energy. Like the sun, stars generate energy by fusing hydrogen into helium in their cores. A star that fuses hydrogen faster will be hotter because it's making more energy. The rate of fusion depends on the pressure in a star's core. More massive stars can squeeze their cores harder, so they fuse faster and get hotter than low-mass stars. It's pretty much that simple, and that explains the main sequence. Stars spend most of their lives fusing hydrogen into helium, which is why the main sequence has most of the stars on it. Those are the ones merrily going about their starry business of making energy. Massive stars are hotter and more luminous, so they fall on the upper left of the main sequence. Stars with lower mass are cooler and redder, so they fall a little lower to the right, and so on. The sun is there too, more or less in the middle. What about the other groups? Well, the stars on the lower left are hot, blue-white, but very faint. That means they must be small, and we call them white dwarfs. They're the result of a star like the sun eventually running out of hydrogen fuel. We'll get back to them in a future episode. The stars on the upper right are luminous but cool. They must therefore be huge. These are red giants, also part of the dying process of stars like the sun. Above them are red supergiants, massive stars beginning their death stage. You can see some stars that are also that luminous, but at the upper left. Those are blue supergiants. They're more rare, but they too are the end stage for some stars. And again, we'll get to them soon enough in a future episode. But I'll just say here that it doesn't end well for them. But on a brighter note, we literally owe our existence to them. And this implies something very nifty about the HR diagram. Stars can change position on it. Not only that, but massive stars versus low-mass stars age differently and go to different parts of the HR diagram as they die. In many ways, the diagram allows us to tell at a glance just what a star is doing with itself. This difference between the way low-mass stars like the sun and higher-mass stars age is actually critical to understanding a lot more about what we see in the sky. So much so that they'll be handled separately in later episodes. I'm sorry to tease so much about what's to come, but this aspect of stars, finally understanding them physically, was a major step in astronomy, leading to understanding so much more. And don't you worry, we'll get to all that. Today you learned that stars can be categorized using their spectrum. Together with their distance, this provides a wealth of information about them, including their luminosity, size, and temperature. The HR diagram plots stars' luminosity versus temperature, and most stars follow along the main sequence, where they live most of their lives. Crash Course Astronomy is produced in association with PBS Digital Studios. Head over to their